In this lesson, we are going to talk about the binomial probability distribution. So our first objective here is to determine whether a probability experiment is a binomial one. So the binomial probability distribution is a discrete probability distribution that describes probabilities for experiments in which there are two mutually exclusive outcomes. These two outcomes are generally referred to as success and failure, and experiments in which only two outcomes are possible are referred to as binomial experiments, provided that certain criteria is met. So the criteria for a binomial probability experiment has to meet these four things. The experiment has to be performed a fixed number of times, and we refer to that as trials. So a fixed number of times, which are called trials. The trials must be independent. Okay, so the trials are independent. So the outcome of one trial will not affect the outcome of the other trials. For each trial, there's two mutually exclusive outcomes, either what we refer to as success or failure. And the probability of success is the same for each trial of the experiment. All right, it has to meet those four criteria in order for us to consider it a binomial probability experiment. So we're going to let the random variable capital X be the number of successes in n trials of a binomial experiment. Then capital X is called a binomial random variable. So some notation here we're going to denote first is little n represents the number of trials. The probability of success is represented by the letter P. The probability of failure then would be 1 minus P, and I sometimes refer to that as Q. So if I happen to do that, Q is representing the probability of failure. The lowercase variable x is representing the number of successes. And that number has to be between 0 and the number of trials, n. So you could have 0 successes, or we could have up to all of our trials being successes. And what we will be finding is the probability that x is equal to something. We might be finding the probability that little x is greater than something, less than something, less than or equal to something, okay? That's what we are looking to find. So for the first example here, we are going to determine which of the following probability experiments represents a binomial experiment. If it's not binomial, then we're going to state why. So we need it to pass that four criteria. So in A, a random sample of 15 college seniors is obtained, and the individuals selected are asked to state their ages. Okay, well, there's a couple of things here, but one is no, this would not be binomial. Because first of all, if you're just selecting ages, that's not a success or a failure. Plus, the random variable age is continuous. And the variable must be discrete in order to be binomial. For part B, an experimental drug is administered to 100 randomly selected individuals, which the number of individuals responding favorably recorded. So we don't know what responded favorably is. Maybe they're interested in whether you have high blood pressure or not. So maybe high blood pressure would be success. Not having high blood pressure would be a failure. So this is done a fixed number of times. The trials are independent. there is success or failure, and the probability of success is the same for all the trials. Okay, there's nothing that changes that. Therefore, this would be a binomial probability experiment. For part C, a poll of 1,200 registered voters is conducted in which the respondents are asked whether they believe Congress should reform Social Security. So you're thinking of these 4 criteria. Is there a fixed number of trials? Yes, it's 1,200. Are they independent of each other? Yes. Is there success or failure? Yes. In this case, success would be reform, failure would be not reform, and the probability of success is the same, so therefore this is binomial. And part D, in a town with 400 citizens, 100 randomly selected citizens are asked to identify their religion. The number who identify with a Christian religion is recorded. Okay, so if we're kind of thinking of our criteria, there's a fixed number of times. There does seem to be success or failure, where success would be Christian religion, failure would be not Christian religion. The probability is probably the same. However, because we're doing this in a town with only 400 citizens, and we're selecting from that town only, these trials are not independent. So this is not binomial. All right, most likely you got a town. There's probably a religion associated with that town if it's a small town. So the trials would not be independent. All right, at the bottom here, just be cautious. I want to let you know that success does not mean good and failure does not mean bad. Success is just whatever we are interested in, and failure is whatever would be the opposite, that we're not interested in. So the example they use here is maybe we're interested in the number of 18-year-olds in an accident. Then the probability of success would be the 18-year-olds in an accident. Our failure, so to speak, would be those not in an accident. So don't think of success and failure as good or bad. I mean, it could be, but it's not, it does not have to be that way. So success is whatever we're interested in. Our second objective here is to compute probabilities of binomial experiments. So here, if you look at this example, we have the Bureau of Transportation Statistics. The proportion of on-time flights at Las Vegas's McCarran International Airport was 0.8. Suppose that 4 flights are randomly selected from April 2019, and the number of on-time flights X is recorded. So that's what this data is showing here. So if the first trial could have been a success or it could have been a failure. From there, the second trial could have been a success or failure, and then each of those could have been a success or failure, and so on. So these are the different outcomes there. And then stated over here, we just have the number of successes. So all 4 were on time, 3 were on time, the last one was not. On time, not on time, so on. So it says construct a probability distribution for the random variable x using the tree diagram. Okay, well, if we were doing this all by hand, we're going to end up getting to a formula here. If I was finding the probability that the number of successes was 0, then I'm going to look up here and see where was the number of successes 0. And that was just this one time here, okay? All flights were late on all 4 trials. So I'm taking the probability that the first is a failure, and the second's a failure, and the third's a failure, and the fourth a failure. because these are independent events, we will just multiply their probabilities together. So the probability of it being a failure is 0.2. We found that by 1 minus 0.8. When we multiply all those together, we get 0.0016. So the probability that there are no successes is 0.0016. So that's what we would fill in for our probability distribution table when x is 0. So now if we want to find when x is 1, then that means there's one success. So I'm going through and looking here. Here's a time where there was one success. Here's a time where there was one success. Here's a time, and there's another time. So there's 4 total times there. So our options was success and then 3 failures, a failure and then a success and then 2 failures, or fail, fail, success, fail, or the first 3 trials were failures and the last one was a success. Because they are mutually exclusive, we will use the addition rule. So we're taking this probability plus this probability plus this, and for each of those, they are independent, so we are going to multiply their probabilities together. So if you see here, we're really taking 4 times the probability of success, and then we are taking the probability of a failure to the 3rd power, because it's the same for all of them. So that probability is 0.0256. Okay, you can see here we're kind of working our way towards the formula we're going to work with. Here we're finding the probability that the number of flights on time is equal to 2. Well, if you look, there was 1, 2, 3, 4, 5, 6 times that occurred. So there's 6 different ways that could happen. So we took the number of ways it could happen times the probability of success raised to the number of successes, which is 2, times the probability of failure raised to the number of failures, which is 2. That probability is 0.1536. Do the same thing for the probability that there are 3 successes and the probability that there are 4 successes. So that's how we got these numbers for our probability distribution table. Now, lucky for us, we've just kind of created this formula here. Okay, so P of x is equal to n choose x, so we're using a combination because order does not matter, times p raised to the x times 1 minus p raised to the n minus x. So let's talk about what those things mean. Oh, I'm going to rewrite this off to the side. We have n choose x times the probability to the x power times 1 minus p raised to the n minus x. Okay, so n choose x, that's the number of ways success is possible. Okay, so number of ways for x successes. P is representing the probability of success, and x is the number of successes. And then 1 minus p is the probability of failure. And then n minus x is representing the number of failures. All right, so those are the things that we're going to be plugging in to the formula. And we'll also be using StatCrunch. All right, so for our probabilities, we might not be just finding the probability that x is equal to something. We might be finding the probability that x is at most something. Well, at most is less than or equal to. So we just want to make sure that you understand the different phrases that match with the math symbols. So if you don't remember those, that's something you might want to refresh on. All right, so in example 3, a binomial probability experiment is conducted with the given parameters. Compute the probability of little x successes in the n independent trials of the experiment. So we have no context here. We're just given what n is, what p is, what x is, and we're going to use the formula and StatCrunch, and I'm going to show you how to use a table. Okay, so if we're using our formula here, well, when x is equal to 3, we're finding the probability that little x is equal to 3. That's what we're calculating. So by hand, we're going to do 10 choose 3 times the probability of success, which is 0.4, raised to the number of successes, which is 3, times the probability of failure is 1 minus the probability of success. So 1 minus 0.4 is 0.6. Raised to the n minus x would be 10 minus 3, which is 7. So this is the number 1 minus p. This is the number n minus x. Notice my exponents, 7 plus 3, add up to my total number of trials. That's going to be true every time. All right, so if we are typing this into our calculator, we are doing math, going over to probability. We're doing a combination. So we have 10 choose 3 times 0.4 raised to the third power times 0.6 raised to the seventh power. So the probability that the random binomial variable x is 3 is about 0.2150. Okay, so if we are doing this in StatCrunch, I'll go ahead and write here, we're going to go to Stat, we're going to go to Calculators, and we're going to go to Binomial. Alright, so you're just opening up StatCrunch with no data in it. We're going Stat, Calculators. Notice there's a whole bunch of different types here. We are working with binomial today. So n is 10. Our p is 0.4. Let's see. There we go. And if you click in that, you can select your symbol or equal, find the probability that it's equal to 3. Hit compute, and that's the 0.2150 that we got. It also shows you on the graph what we are interested in. So we're interested when x is equal to 3 here. You can also kind of see your distribution shape there. It's getting pretty close to normal, or pretty close to symmetrical or bell-shaped. Maybe a little skew out here to the right. All right, we will explore that a little bit later. So if we do that in StatCrunch, we get the same thing. And then a third way we can find the probability is using the tables in the appendix of your book. So when you guys open up My Math Lab, you can click on eText Contents, and then I'm going to view the eText that mirrors your book. All right, the appendix is at the very back of the book. All right, so if I click table of contents, I'm going to go down to the very bottom here. Oh, maybe. And I'm going to click on Appendix A, which is the tables. And we were told to go to tables 3 and 4, so this is table 1. There's table 2 we've used before. Okay, so table 3 here says the binomial probability distribution. So it shows you got P up here, you got your n values, your x values. So we know our n is 10, so I'm looking, and 10 is not on this page, so I need to go to the next page. So when n is 10, I'm looking at all these values down here. Okay? So then at the top here, this is our probability of success. So ours was 0.4. So I'm going to be looking at this column. And I'm going down. So I'm looking at this column when n is 10. And then I'm looking when x is 3. If I come across here, you can see right above my cursor there is 0.2150. So it is right there in the table for us. Okay, so find the n value first, find the p value, and then go to the row that matches x. And it's the same number. Okay, so for part B here, now we have n equal 9. The probability of success is 0.2. And we want to find the probability that x is less than or equal to 3. So we are finding the probability that x is less than or equal to 3. Well, that means we're looking for the probability that x is equal to 3, or x is equal to 2, or x is equal to 1, or x is equal to 0. And we're just going to use the addition rule since these are independent here. So we're really finding the probability that it's 3, plus the probability that it's 2, plus the probability that it's 1, plus the probability that it is 0. Well, if I'm doing this by hand, I'm going to use the formula for each probability. So the probability that x is 3 would be 9 choose 3 times 0.2 raised to the third power times the probability of failure is 1 minus 0.2, which is 0.8. And it's going to be raised to the n minus x, so 9 minus 3 would be 6. Plus, I'm going to do this for the probability that it's 2, so I'm going to do 9 choose 2 times 0.2 to the second power times 0.8 raised to the 7th power. Plus, for the probability that it's 1, I'm doing 9 choose 1 times 0.2 raised to the first power times 0.8 raised to the 8th power. And then the probability it's equal to 0 is 9 choose 0 times 0.2 raised to the 0 power times 0.8 raised to the 9th power. Again, if you look at all of these, my exponents add to the total number of trials each time, which is 9. So you can crunch that all into your calculator and you would get 0.9144. Using StatCrunch, we'll go back in to StatCrunch here. Now our n is 9. P is 0.2. And we're finding the probability that x is less than or equal to 3. And there's our value, 0.9144. And again, if you look at the graph here, it's showing us this is the probability we're interested in, and this would definitely be skewed right. All right, when we do this in the table, table 4 shows the cumulative probability. So the row labeled 3 would show the probability that x is less than or equal to 3. It's taking that x value and adding up all the ones before it. Okay, so for here we would use table 4 because it shows the cumulative probability. So row 3 shows the probability that x is less than or equal to 3. So if we go take a look at that, so that's table 3 continued. Table 3 continued. Okay, here's table 4, which it says cumulative binomial probability distribution. So our n is 9, so that's going to be on the next page. Okay, so here n is 9. Our probability is 0.2, so we're looking at this column here. And this is cumulative, so it's taking the one before and adding it to it. So when x is less than or equal to 3, the probability is this 0.9144. All right, part C. Now we have n is equal to 7. Probability of success is 0.5, and we're looking for the probability of x being greater than 3. So the probability that x is greater than 3, well, we're only doing 7 trials, so we're only going to go up to 7. So really we're taking the probability that x is 4, plus the probability that x is 5, plus the probability that x is 6, plus the probability that x is 7. So using the formula, we would do 7 choose 4 times 0.5 to the 4th power. Probability of failure is also 0.5, and this would be raised to the 3rd power. Plus, we would have 7 choose 5 times 0.5 to the 5th power times 0.5 to the 2nd power. Plus 7 choose 5 times 0.5. Oops. Now we're on to 7 choose 6. Probability that it's equal to 6. So 0.5 to the 6th power times 0.5 to the 1st power plus 7 choose 7 times 0.5 to the 7th power times 0.5 to the 0 power. So my first one represents the probability that it's 4. Second one is the probability that's 5. Third one is the probability that it's 6. Last one is the probability that it is equal to 7. And if you type that all in, you would get 0.05. So looking at that in StatCrunch, all right, now we just have n being 7. Probability is 0.5. And we're finding the probability that x is greater than 3, and it's 0.5. So there you can see we have our symmetrical bell-shaped curve. This is the probability we're interested in. Greater than 3 would be 4, 5, 6, or 7. If we are looking at that table, we can use table 3 or table 4. Okay, but if we use table 4, then the probability that x is greater than 3 would just be 1 minus the probability that x is less than or equal to 3. So if we go look in that table, we're going to see that the probability x is less than or equal to 3 is 0.5. So 1 minus 0.5 is 0.5. Your other option using table 3 is to add up all the probabilities. So you would find the probability that x is 4, add that to the probability that x is 5, add that to the probability that x is 6, and add that to the probability that x is 7, and you're going to get 0.5 as well. So either way works just fine. Okay, so now let's apply this to some context. So example 4, in a recent poll, the Gallup organization found that 45% of adult Americans believe that the overall state of moral values in the United States is poor. Suppose a survey of a random sample of 25 adult Americans is conducted, in which they are asked to disclose their feelings on the overall state of moral values in the United States. Okay, so this is binomial. N is the 25. Our probability of success is the 45%, which is 0.45. And then the probability of failure, remember, which I typically refer to as Q, is 1 minus 0.45, which is 0.55. Okay, we may not need that, we might, so I just leave it there. So in part A, it says find and interpret the probability that exactly 15 of those surveyed feel the state of morals is poor. So we're finding the probability that x is equal to 15 because it says exactly 15. We're talking about the morals being poor, which is the 45%. So we're using P being 0.45. So if I'm writing this out by hand, I'm going to do 25, choose 15, times the 0.45 to the 15th power, times the 0.55 to the 10th power, because that would be the number of failures. I'm just going to use StatCrunch, okay? So if I type this in the StatCrunch, we got N to be 25. Probability is 0.45. And we're finding the probability that x is equal to 15. Compute. And it's 0.0520. So if we interpret that, then what that means is in 100 trials of this study, we would expect 5 trials, because it's 5%, so 5% of 100 is 5. So we would expect 5 trials to result in exactly 15 adult Americans who feel the state of morals is poor. All right. So for part B, find and interpret the probability that no more than 10 of those surveyed feel the state of morals is poor. So we are finding the probability that no more than 10, so that would be x is less than or equal to 10. So in StatCrunch, my N and my P stay the same. I'm finding the probability that's less than or equal to 10. Compute, and that is 0.3843. So if we interpret that, I'm going to copy and paste this here, change some things. In 100 trials of the study, we would expect 38 trials to result in, let's see here, no more than 10 adult Americans who feel the state of morals is poor. Okay, so 38% of 100 is how we get the 38 trials we're talking about there. Part C, find and interpret the probability that 13 or 14 believe the state of morals is poor. So we are finding the probability that x is equal to 13 or x is equal to 14. Now, we could do those two separately and add them together. However, that's the same thing as finding the probability that x is between 13 and 14. Okay, so we could find the probability that x is 13 and add that to the probability x is 14. However, if we do this now in StatCrunch, we're just going to choose between. Alright, so if I go to StatCrunch, see up here, there's standard and between. Right now we're on standard. If we click on between, my n is 25, my p is 0.45. Now we're looking for an x value between 13 and 14. Compute that, and we get 0.2103. So to interpret this, in 100 trials of the study, we would expect 21 trials. Okay, we would expect 21 trials to result in 13 or 14. Adult Americans who feel the state of morals is poor. Okay, so part D, would it be unusual to find 20 or more adult Americans who believe the overall state of the moral values is poor in the United States? Why? Okay, so first we need to know, well, what is the probability that x is greater than or equal to 20? 20 or more. So if we do that in StatCrunch, go back to standard, and we'll go greater than or equal to 20, which is 0.0004. I'll even call it 38 just so we know. That number is less than our 0.05, our 5% unusual cutoff. So we would say yes, it would be unusual. Since the probability that x is greater than or equal to 20 is equal to 0.00038, which is less than 0.05. Okay. All right, moving on to objective 3, we are going to compute the mean and standard deviation of binomial random variables. All right, so here we have the mean of x is equal to n times p. And then the standard deviation of the random variable binomial variable x is the square root of, I call that n times p times q. So you're taking n times p times 1 minus p, which I refer to as q. Okay, so in March of 1995, the Harris poll reported that 80% of parents spank their children. Suppose a recent poll of 1,030 adult Americans with children find that 781 indicated that they spank their children. If we assume parents' attitudes towards spanking has not changed since 1995, how many of the 1,030 parents surveyed would we expect to spank? Do the results of the survey suggest that parents' attitude towards spanking may have changed since 1995? Okay, well, we want to know how many would we expect. That's just your mean. Okay, so some things to point out here. The probability of success. We're referring to success as spank their kids. That is equal to 0.80. And we know that n is 1,030. So to find the expected value of x, we're just finding the mean of the random variable x, which when binomial is n times p. So we're taking 1,030 times the 0.80. Type that into your calculator and you get 824. Okay. So we would expect 824 parents out of 1,030 to spank their children. Okay, so that answers how many would we expect. Then it asks, do the results of the survey suggest that parents' attitude towards spanking may have changed since 1995? Okay, so to determine this, we're going to look at that bell-shaped curve or the empirical rule. So if you remember, in the curve, this would be our mean. And then this would be plus 1 standard deviation, plus 2 standard deviations, and then plus 3 standard deviations. This would be minus 1 standard deviation, minus 2 standard deviations, minus 3 standard deviations. Well, within 2 standard deviation lies 95% of the data. So that would mean that the other 5%, which would make it unusual, so this is considered usual, this is considered unusual, and this is considered unusual. So remember, this portion out here is 2.5%, and this portion to the left is 2.5%. So together that would represent 5%, which would make it unusual. So to determine if this is unusual, we're going to take the mean and add 2 standard deviations, and take the mean and subtract 2 standard deviations to see where 95% of the data should lie. Well, in order to do that, we need the standard deviation. All right, so standard deviation of x is equal to the square root. I call it n times p times q. So that's going to be the 1,030 times 0.8 is success, meaning spank, not spank is 0.2. When you do that, you get approximately 12.8. Okay. So I'm going to take the mean plus 2 standard deviations, and I'm going to take the mean minus 2 standard deviations. So the mean plus 2 standard deviations is going to be 824 plus 2 times the 12.8. Minus is going to be 824 minus the 2 times 12.8. All right, so let's see, 824 minus 2 times the 12.8 is 798.4. If we do the same thing, I do plus 849.6, so 798.4. And then 849.6. Okay, so that's what these two numbers would be. This would be 798.4. This number here would be the 849.6. So we want to know, is the expected value 824? No, sorry, not 824. What number are we interested in? The results of the survey suggest that parents' attitude towards spanking may have changed. We're looking at the 781. Okay, so right here. There we go. Okay. So in the recent poll, it said that 781 indicated that they spanked their children. So the expected value, all this is what we used based on the previous information, the previous data. Okay, 80%. We want to know, has that changed? Well, the 781 would lie somewhere in that area. So it's more than 2 standard deviations away. So it is unusual. So we would say that the results suggest that parents' attitudes about spanking has changed. Since 781 is more than 2 standard deviations away from the mean. Of our 824. Okay, so objective 4, we're going to graph a binomial probability distribution. So to graph a binomial probability distribution, it says first find the probabilities for each possible value of the random variable and then follow the same approach that we used previously to graph discrete probability distributions. So this example is kind of already done out for us. We're just going to take a look at it. So in graph A here, we're graphing the binomial probability distribution with n equals 10 and a probability of 0.2. Comment on the shape of the distribution. Well, here is what that graph looks like. So if we look at this distribution, you can see that it is skewed right. For table B, we're graphing it with n equals 10, but now our probability is 0.5. When you look at that graph, you can see that it is more symmetrical or bell-shaped.
I want my elephant in my pit. I don't like it.
Okay, so notice when P was 0.5.
I want to be.
Okay, so when P is 0.5 and N is 10, we got a symmetrical shape. Up here, P was 0.2. N was also 10. If we look at C, N is 10 and P is 0.8. And this one is skewed left. Okay, so if you look there, based on those results, we can conclude that the binomial probability distribution is skewed right if p is less than 0.5, approximately bell-shaped if the probability is equal to 0.5, and skewed left if the probability is greater than 0.5. Okay, and notice that the first graph A and the third graph C are mirror images of each other. Okay, so that's kind of how the role of what probability plays on a specific number of trials. So if we look down here in figure 12, might be a little hard to see, but now it's our n value is changing. So we have probability of success is 0.2 with n being 10. Now n is 30. Now n is 70. So even though the probability is 0.2 for all of them, you should be able to see the more trials there are, we get closer to asymmetric or bell-shaped probability. All right. So for a fixed p, as the number of trials n in a binomial experiment increases, the probability distribution of the random variable capital X becomes bell-shaped. So as a rule of thumb, we can say if n times p times 1 minus p, so if n times p times q is greater than or equal to 10, then the probability distribution will be approximately bell-shaped. So that's why in that last one, to determine if it was unusual or not, we took the mean plus or minus 2 standard deviations, and if it was outside of that, then we said it was unusual. Okay? So if our value we're talking about lies within 2 standard deviations, it's not unusual. And if it doesn't, then it is unusual. All right, and example 6 here, which is our last example. Part A, well, first of all, a binomial probability experiment is conducted with the given parameters n equals 6 and p equals 0.3. Part A says to construct a binomial probability distribution. Okay, well, that's where we have x and p of x. I'm going to use StatCrunch to do this. All right, so I'm going to go to StatCrunch. I'm going to let n equal 6. P is going to equal 0.3. And then I'm going to find x is equal to make my probability table. I'm going to do 0, and then I'm going to go all the way through 6. So when it's 0, we have a probability of 0.1176. Oops. Okay, x could be 1, x could be 2, 3, 4, 5, and 6. So I'm going to go back and do that for each one. So the probability of x being 1 is 0.3025. I'm going to do the same thing, plug in x equals 2, and we would get 0.3241. When x is 3, 0.8152. When x is 4, 0.0595. When x is 5, 0.0102. And x is 6 is 0.0007. All right. Part B, compute the mean and standard deviation of the random variable using methods of 6.1. Okay, so that's where we use the probability distribution table. So the mean of x is going to be the sum of x times p of x. So we're going to take 0 times 0.1176 plus 1 times 0.3025 plus 2 times 0.3241 plus, we're going to do that for all of them up to the last one, which would be 6 times 0.0007. Type that all into your calculator and you would get the mean to be 1.8. Now we're going to calculate the standard deviation, which for that we took the square root of the sum of x squared times p of x minus the mean of x squared. So that would be taking the square root of, we would take 0 squared times the probability of x being 0, which is 0.1176, plus 1 squared times 0.3025, plus all the way up to 6 squared times 0.0007, and then we subtract the mean of x squared, which is 1.8 we just found. Square that. Okay, so typing that into your calculator, if we just did the sum of x squared times p of x, that's 4.4979 minus 1.8 squared. We would get 1.1 to be our standard deviation. Okay, so now part C says compute the mean and standard deviation using the methods of this section. So the mean for a binomial is n times p, which would be 6 times 0.3, which is equal to 1.8. Comparing, same exact thing we got above. The standard deviation is the square root of n times p times q. So that would be 6 times 0.3 times 0.7. Take the square root of that, and you get 1.1, which is exactly what we got before. Okay, so notice both ways work. So it's nice to have your options there depending on what information you have maybe in front of you. And then last, part D, draw a graph of the probability distribution and comment on its shape. So if we're going to draw a graph here, our y-axis is our p of x, and then down here is just our x, or our number of successes. So I'm going to go by 0.05. Keep going to 0.35. Alright, and then our x's, we have 0, 1, 2, 3, 4, 5, and 6. So the probability that x was 0, if we go back and look at our table, was 0.1176, so we'll go 0.12. So maybe like here. X being 1, the probability was 0.30. For 2, it was 0.32. For 3, it was 0.19 approximately. X equal 4 was 0.06. X equal 5 was 0.01. And x equal 6 was 0.0007, so that was really small. Alright, so there's the graph, and it says to comment on its shape. That appears to be skewed right. Okay, which kind of makes sense. We have a low number of our success is 0.3. But if we, instead of had 6 trials and maybe had, 100, it would look more symmetrical. And that's all that I have on the binomial probability distribution.